Band. I'm Michiban Irunjano, Michiban Hotel.
I'm Michiban Sena. I am Michiban Bayot.
And we are the Cluster 3.
Today, we will be discussing electricity and magnetism. It's easy to see the uses of electricity around you. In fact, there are charges around your computer, your house, and your city. Electricity is constantly following through all the wires in your town. This is also in your flashlight. That kind of electricity created by batteries is called direct current. The other major type is found in the outlets of your home. That household form is electricity is called alternating current. There are two types of charges, positive and negative. Like charges repel and opposite charges attract. For example, two positive charges go to each other will be pushed away from each other. On the other hand, one positive charge and one negative charge both near each other will be pulled towards each other. It is the principle on which electrostatic is based. There are many examples of electrostatic phenomena, from those as simple as the attraction of the plastic wrap to your hand after you remove it from the package, to the apparently spontaneous explosion of grainy cellulose, to damage of electronic components during manufacturing, to the operation of photocopiers and others. Electrostatic involves the buildup of charges in the surface of objects due to contact with other surfaces. The atomic structure. Matter has a mass and takes up space. Atoms are basic building blocks of matter and cannot be chemically subdivided by ordinary means. The word atom is defined from the Greek word which means indivisible. The Greek is concluded that matter could be broken down into particles too small to be seen. These particles were called atoms. Atoms are composed of three types of particles: proton, neutron, and electron. Electron. The electron is negatively charged with a charge of negative 1602 times 10 raised to negative 19 coulombs. For convenience, the charge of electron is usually simplified and referred to as negative 1. Like this. Negative 1602 times 10 raised to negative 19 coulombs, or simplified as negative 1. The second is the proton. The proton has a charge of positive 1 electron charge, or equals to 1.602 times 10 raised to negative 19 coulombs, or simplified as 1.0602 times 10 raised to negative 19 coulombs. Neutron. Neutron has no charge. Its electricity is neutral. No, because atoms have an equal number of electrons and protons, they have no net electrical charges or charge. Protons and neutrons are located in the nucleus, the center of the atom, while the electrons reside in the orbit around the nucleus. The nucleus is smaller than the atom. Majority of the space of an atom is the space in which the electrons move around. Take note, electrons are attracted to the protons and the nucleus by the force of attraction between particles of opposite charges. The mass of an atom is extremely small. The unit of mass is used to describe as atomic particles is the atomic mass unit, or AMU. An atomic mass unit is equal to 1.66054 times 10 raised to negative 24 grams. Simplified like this. 1.66054 times 10 raised to negative 24 grams. How do the different substances particles compare in terms of mass? Simplify, proton is equals to 1.0073 atomic mass unit, but neutron is equal to 1.007 atomic mass unit, and electron is equal to 5.486 times 10 to negative 4 atomic mass units.
Lips, wow. Hear the sound of your body drip, drip.
From this comparison, we can see that the mass of the proton and neutron are nearly identical. The nucleus, which equal to protons and neutrons, contains virtually all of the mass of the atom. The electrons, while equal and the opposite in charge, the protons, have only 0.05% the mass. The size of an atom is quite small. The typical range for atomic diameter is between 1 times 10 raised to negative 10 and 5 times 10 raised to negative 10 meters.
To be a minute man, maybe you're just like a
Coulomb's law. The interaction between charged object is a non-contact force that acts over some distance of separation.
I'm gonna lick all night, yeah, when I'm inside.
Electric field is defined the electric force per unit charge. The direction of the field is taken to be the direction of the force it will exert and positive test charge. The electric field is radically outward from a positive charge and radically inward a negative point charge.
Bring your back like it's limbo. I'ma make you feel like an info tonight.
What is electric potential? Electric potential can be defined as the capacity for doing work which arises from position or configuration. In the electric case, a charge will exert a force on any other charge, and potential energy arises from any potential.
This booty and thighs, I don't want to be
What is zero potential? The nature of potential is that the zero point is arbitrary. It can be set like the origin of a coordinate system. That it is insignificant when the zero of potential is set, then every value of potential is measured with respect to the zero. In another way of saying, it is that the charge at the change in potential reach physical significance. The zero of electric potential or voltage is set for convenience, but there is usually some physical or geometric logic to the choice of the zero point. For a single point charge or localized collection of charges, it is logical to set the zero at infinity. But for an infinite line charge, that is not a logical choice, since the local value of potential would go to infinity.
Braxton, you can't deny you wanna break my back in two. What you wanna do? Look at you.
One is capacitance and dielectrics. Capacitance is the ratio of the magnitude, the change in the capacitor to the magnitude, by the potential difference in the capacitor. It is always a positive quantity. It is a measure of the ability of a device to store charge and electrical potential energy. Unlike a power supply, which also maintains an electrical potential between 2 points, it is limited by the fact that it can be stored only a finite amount of charge.
Kiss both sets of lip.
What is dielectrics? Dielectrics is a material that when used in a capacitor increases the efficiency of the capacitor. Example of dielectrics materials: dry glass, mica, porcelain, paraffin paper, rubber vulcanized, transformer oil.
I'm at a payphone. The sun goes down, the stars come.
Electric current could be a flow of electrical charge. Electrical phenomenon flows once there's voltage given across a conductor. In electrical circuits, this charge is communicated by moving electrons in an exceedingly wire. It may be carried by an ion solution by each ions and electrons like an exceedingly plasma. The SI unit for measure an electrical current is that the ampere, which is that the flow of electrical charge through a surface at the speed of 1 coulomb per second. Electrical phenomenon is measured as using an ampere. There are two types of electrical current. One is DC called direct current. Direct current doesn't change direction. Example of it is batteries. The second electrical current is called AC, which is called alternating current. Always changes direction. One of the example is electrical outlet. Remember that the electric current always been negative.
Let's go, turn up the music 'cause the song just came on. Here and now, I'm talking here and now. Let's go, turn up the music.
Electric power is a rate at which electric energy is transferred. Electric power is measured by capacity and is commonly expressed in megawatts. A megawatt is 1 of the million watts. Energy generated through the conversion of other forms of energy, such as mechanical, thermal, or chemical energy. Electric energy is unveiled for many uses, as for lighting computer operation, motive power, and entertainment applications. For other uses, it is competitive, as for many industrial heating applications, cooking, space heating, and railway traction.
Magnetism is a force where objects are attracted or repelled to one another. Usually these objects are metals such as iron. It is due to the material field which is caused by moving electrical charged particles. It is also inherent in magnetic objects such as magnet.
I let it fall, my heart.
Hi everyone, I'm Mr. Fullerton, and today I'd like to talk to you about magnets and magnetic fields. Our goals are going to be to explain how magnetism is caused by moving electrical charges, to describe the magnetic poles and interactions between magnets, and finally to draw magnetic field lines. Now, what is magnetism? Magnetism is a force caused by moving charges. Permanent magnets are caused by the electrons, the charges in the atoms, spinning in roughly the same direction. Not all of them, but a majority of them spinning in the same direction gives you a net magnetic field in that object. Now there's really a lot more complexity to it than that, but that's a first pass explanation of how magnetism works in a permanent magnet. In a non-magnet, the spin of the electrons is much more random, so all the little individual magnetic fields from those moving charges cancel out. In an electrical magnet or an electromagnet, the electric current provides the moving charges to create the magnetic field. So, what type of field is present near a moving electric charge? An electric field, a magnetic field, both, or neither? Well, because it's a moving charges create magnetic fields. We must have a magnetic field, and since it is an electric charge, you also have an electric field. So the correct answer must be 1, both. You have an electric field because you have an electric charge, and because it's moving, you get the magnetic field. Now, magnets are polarized, meaning every magnet has a north and a south. If you happen to have a magnet that has a north and a south, and you cut it in two, you actually get two magnets that each have a new north and south. You can't ever cut a magnet in two and have just a north and just a south. The north end of a magnet points toward the Earth's geographic North Pole, and the south end of a magnet points toward the Earth's geographic South Pole. Now, again, there are no magnetic monopoles. You can never have a north without a south. Materials can be classified as magnets, non-magnets, or magnetic attractables. Magnets create magnetic fields. Magnetic attractables are things like a paperclip, for example, that you can pick up with either end of a magnet, a north or a south, but it's not a magnet in its own right. And non-magnets are things like a block of wood. If you put a magnet near a block of wood, you really can't pick it up. So, north and south poles can attract magnetic attractables, but you can't repel from a magnetic attractable. The other thing you need to know about magnetic forces is the closer the objects are, the stronger the magnetic force. The further apart they are, the weaker the magnetic force. So, another sample problem. We have here in the diagram a half-kilogram bar magnet and a 0.7 kilogram bar magnet with a distance of 0.2 meters between their centers. Which statement describes the forces between the bar magnets? It asks us about gravity and the magnetic force. Well, right away we know gravity can only attract. So a gravitational force that repulsive doesn't work, so that eliminates 1 and 2. Now, because the closest poles are the norths, those will have the strongest forces, and those are like poles, so they will repel. So the gravitational force is attractive, gravity always attracts, and the magnetic force is repulsive. Answer number 3. Another problem, a student is given 2 pieces of iron and told to determine if one or both of the pieces are magnets. First, the student touches an end of one piece to one end of the other, and the 2 pieces of iron attract. That tells you that you must have at least one magnet, and the other one is either a magnet or a magnetic attractable. Then the student reverses one of the pieces and again touches the ends together, and they attract again. Well, if they attract from both ends, that means one must be a magnet, the other must be a magnetic attractable. If they were both magnets, when you flipped one, you would get a repulsive force. So what you know is that at least one of the pieces is a magnet, and the other is a magnetic attractable. All right. Here we have 2 ring magnets placed on a pencil. Magnet A remains suspended above B as shown. Which statement describes the gravitational force and the magnetic force acting on A due to B? Well, again, the gravitational force is always attractive, so we can get rid of anything that has gravitational force as repulsive. Because A is being suspended above B, that must mean that B and A are repelling each other in order to hold A up above B. So we know the gravitational force is attractive, the magnetic force must be repulsive. Answer number 1. Now, magnetic field lines or magnetic flux lines show the direction the north pole of a magnet would tend to point if placed in the field. And this is very similar to what we did with electric field lines or gravitational field lines. Magnetic field lines are drawn as closed loops, and the magnetic field is strongest in areas of the greatest density of magnetic field lines. So down here on the bottom left, we have a picture of a bar magnet with the north and the south. The magnetic field lines always run outside the magnet from north to the south. Inside the magnet, they run from south to north to make that closed loop. But outside the magnet, those field lines run north to south. So in this problem, the diagram shows the lines of magnetic force between 2 north magnetic poles. At which point in the magnetic field is the magnetic field strength greatest? And our choices are A, B, C, or D with those little dots. Well, the magnetic field strength is greatest in areas of the most field lines, the greatest flux density we call that. And I see the greatest density of lines over here by B. So B must be our answer. It has the greatest magnetic field strength because it is located in the highest density of magnetic field lines. Hopefully this gets you started with magnets and magnetic fields. If you're looking for more help, need more information, want to go more in depth, check out aplusphysics.com. Thanks for your time and make it a terrific day.
Magnet is an object that exhibits a strong magnetic field and will attract materials like iron to it. Magnets have 2 poles called north and south poles. 2 magnets will be attracted by their opposite poles and each will repel the like pole of the other magnet.
Ampere's law. In classical electromagnetism, Ampere's law, discovered by Andre Ampere in 1826, relates the integrated magnetic field around the closed loop to the electric current passing through the loop. James Clerk Maxwell derived it again using hydrodynamic in 1861 on physical lines of force, and it's now on one of Maxwell Ampere's, which formed the basis of classical electromagnetism.
So falsetto in 3, 2, sway.
Good morning and good night.
The magnetic field in space around the electric current is proportional to the electric current which serves as its source, just as the electric field in space is proportional to the charge which they serve as its source. Ampere's law states that for any closed loop path the sum of length elements times the magnetic field in the direction of the length elements is equal to permeability times the current enclosed in the loop. In electric case, the relation of field to source is quantified to Gauss law, which is powerful tool for circulating electric fields. Important notes: in order to apply Ampere's law, all currents have to be steady. Example, do not change with time. Number 2, one current crossing the area inside the path are taken into account and have some contribution to the magnetic field. Number 3, currents have to be taken with their algebraic sign. Those going out of the source are positive, those going in are negative. Number 4, Ampere's law can be useful when circulating magnetic fields of current distribution with a high degree symmetry.